Okay, so we're in section 5.2. We're going to talk about perpendicular and angle bisectors. But before we get to our theorems, let's have some reminders about the vocabulary we're using here. Perpendicular. What do we mean when we say perpendicular?
90 degrees.
Has to do with a 90-degree angle? Two segments that create a 90-degree angle, yeah. Is that what you're going to say? So we have to have two things that are meeting at 90 degrees. So perpendicular means they meet at 90 degrees. And do we remember what our symbol for perpendicular is?
It's like an upside down T.
Upside down T. So when we write that, that's what we mean, perpendicular. How about bisector? Let's break it down. What's bisect mean? Cuts in half. So bisector is something that cuts something else in half. So we're going to talk about perpendicular bisectors and angle bisectors. First theorem is our, I'm going to use a symbol here so we don't have to write words. Perpendicular bisector theorem. And these ideas, they're not complicated ideas. Just we have to pay attention to the details. So what our theorem says is if a point is on the perpendicular bisector, of a segment, and before we write the rest, let's think about what we're talking about when we're talking about a perpendicular bisector. And what is our perpendicular bisector doing to the segment? Cutting it in half and making a 90-degree angle. So both things are happening. It's meeting our segment right in the middle at a 90-degree angle. So this point is on the perpendicular bisector. Then it is equidistant. Equidistant. What do we mean? What does equa mean?
Same distance apart.
Equa means equal distance, same distance apart. Then it is equidistant from the endpoints of the segment. So what we're saying here in pictures is we have this segment. Here's my segment. There are the endpoints of the segment. And we have a perpendicular bisector. So I'm going to bisect the segment at a 90-degree angle. There's my perpendicular bisector. What the theorem is telling us is that any point on this perpendicular bisector, so I'll pick this one. Any point there is equidistant from the endpoints of the segment. So if I draw this and I draw that, those two red segments are going to be congruent. That's what this theorem tells me. And it doesn't matter where I draw the point on the perpendicular bisector. So I could draw another one I could look at this blue point here. Any point on that perpendicular bisector. If I do that, those blue segments are going to be congruent. So I could make any point on that perpendicular bisector, and the segments to the end, to the segments that I draw to the end points here would be congruent.
What's congruent?
The two red segments or the two blue segments.
Yeah.
So any point I draw on this perpendicular bisector, these segments that I draw to the end point here are going to be the same. Because this is halfway between the ends of the segment. So it doesn't matter if I go straight up, or I'm still halfway between the ends of the segments, essentially. So let's really quickly, I'm not going to write a lot more here, but we're saying, let me write a couple of symbols up. I'm going to call this point A, just so we see how another way that this could be written. I'll call it A, B, M, and P, that point up here. We would say that PM is perpendicular to AB, and AM, segment AM, is congruent to segment MB. That's how we know that that's true. And if that is the case, then PA is congruent to PB, MA is congruent to MB, etc., etc. Now, I'm not going to go through the proof, but let's think about how we would go about proving this theorem. Before we knew, let me draw I'm going to draw a green segment here. So there's another point on my perpendicular bisector, that green one. And if we were going to prove that those two green segments were congruent, well, I'm going to look at this little triangle here and this little triangle here. We know that these sides are congruent. Both of these angles are 90 degrees, right? Is there another piece of these two triangles here that we know are congruent? We don't know that yet. That's what we're trying to show. What do you? Right, so this little segment is congruent to itself, right? So the triangles would be congruent by side, angle, side. And then we could say these two green segments are congruent by CP, CTC. So that's how we go about proving this. So that's what the perpendicular bisector theorem tells us. How do we make the converse of an if and then statement? Reverse it. The converse of the perpendicular bisector theorem is true also. So let's reverse it. If a point is equidistant from the endpoints of the segment, what would we write next? If we're going to make the converse of this, then it is on the perpendicular bisector. So that's the converse of this theorem. It is true also. So if we know that these two distances are the same, that tells us the point has to be on the perpendicular bisector. And that's how we make, when we do the construction, our perpendicular bisector construction, where we have our segment and we open up our compass more than halfway, and we make an arc, and we turn around and make the other arc. What we're doing here is making sure that this distance is the same as that distance. And that makes that point on the perpendicular bisector of the segment. That's how that construction works. That's why we do it that way. So they're kind of related. Kind of nice to bring them together. I know my drawing doesn't look like they're congruent, but it's kind of fast. All right, questions there? Let's take a look at the type of problem you might see having to do with perpendicular bisectors. So here is my triangle. And one thing you'll notice in geometry is once we start learning about triangles, we use triangles a lot. Triangles are the friendliest, really the friendliest shape. Triangles and circles.
All shapes are beautiful.
All shapes are beautiful. For geometry, triangles tend to be more useful. And a lot of times we turn problems that have to do with circles into problems that have to do with triangles. So just a preview of what we do. All right, before I do anything else, the way I've drawn that picture, what can we figure out? O bisects segment MP. And what does this little square tell us? It makes a 90-degree angle. So what else do we know about segment OM? It is the perpendicular bisector of segment MP. So OM is the perpendicular bisector. So basically we've solved the problem already. So I'm going to say this side is 6x minus 1, and that side is 3x minus 8. Since OM is the perpendicular bisector, what do we know about segment MN and segment MP? They're equal, they're congruent, their lengths are the same. So I'm going to say, so MN is congruent to segment MP. So I'm just writing out how we're thinking about the problem. If we were trying to prove this, it would be because it's a perpendicular bisector. That would be our reason. But this problem is asking us to, rather than doing a proof, I was just writing out kind of our thought process. Find x. Solve x. Solve for x. So what do? They equal each other. Perfect. 6x minus 1 equals 3x minus 8. And now we're set. We're home free. Solving for x. What do we want to do first? Add 1. We want to get x by itself on one side, so we get 6x equals 3x. Oh, and I'm sorry, this should be a plus. (3x plus 9). Get our x's together by subtracting 3x. 3x equals 9. X equals 3. What if the problem had asked us to find, instead of saying find x, what if it had said find MP? What would we do then? Plug 3 back into the equation. So I would say 3 times 3 plus 8. 3 times 3 is 9 plus 8 is 17. And if I plugged it into this expression, what should I get? Should get 17 also. 6 times 3 is 18. Minus 1 is 7. So that's the way we can check our answer. All right. We good there? Okay.
We do another one? Are we going to see any different models?
They're mostly like this. Yeah, more or less like this. All right, let's look at, let me ask you a question before we do the next piece. If we wanted to, say I wanted to decide how far away I was from the back wall. How would we figure that out? Measure. Would I measure from myself to over by where John is sitting, by the back corner? No?
Straight to the wall.
Straight to the wall. So when we say straight to the wall, what do we mean?
Straight line.
Most direct path, straight line. How do we decide if the line is straight? If I took my tape measure and put it to the wall, how would we know I was going straight towards the wall? There we go. The tape measure would be perpendicular to the wall. So we measure distance is the perpendicular distance. So when we want to find the distance of something, we're going to measure. When we say straight towards, we knew what we meant, but just to be a little more technical, if I want the distance between these 2 points, between here and here, I want to make sure I make that a right angle. So we make sure we measure the distance at a 90-degree angle to whatever we're measuring. So that's going to come into play for our next theory. The angle bisector theorem. I'm having trouble spelling today. Got my own. There we go. All right, so we're talking about angle bisector, or what do we mean? What's the angle bisector? What does it do? Cuts an angle in half. The angle bisector cuts an angle in half. All right, so we're going to say if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So let's draw a picture then. Here is my angle. And I want an angle bisector. So my angle bisector needs to split that angle in half. So if this splits this angle in half, what does it tell us about that piece and that piece? They have to be the same. Splitting in half. Both of those pieces are equal. So let's call this vertex Q and this point on this ray S. So we would say ray QS bisects angle OQ, and sorry, that's not O, that's P. That's part of that word, right? R. Just grabbing letters from anywhere. PQR. So this is the bisector, and let's pick a point on the angle bisector. What this theorem tells us is that if I measure the distance, the perpendicular distance from that point to the side of the angle, and we're making that 90 degrees, and I'm going to do the same thing to the other side of the angle, and we're making that 90 degrees. We're saying those two blue segments are congruent. And that would be true of any point I drew on the angle bisector. If I drew another point here, and I measured the perpendicular distance I'll do that one in green. Perpendicular distance, I'm going at a 90-degree angle to the side of the angle. Those would be congruent also. So any point on the angle bisector that I draw is going to be the same distance to the sides of the angles. And we have to measure that distance at a 90-degree angle. And that, it makes sense. Bisect means it's halfway between the sides of the angle. So this has to be, the point has to be right in the middle of the angle. And that's how we do our construction for our angle bisector. So remember, for our angle bisector, draw a quick sketch here. We make sure an arc across here, and we put our compass here and we measure more than halfway across, and we make an arc there, we measure more than halfway across there, make an arc there. We're making sure that this segment is congruent to that segment. We're making sure they're the same distance from the sides of the angle, and that makes sure that we're on the angle bisector. So that's related to how we do our construction now. All right, questions about what this tells us? The converse of this is also true. So let's write the converse, and then we'll do an example with an angle bisector, and then we will be done. Converse, what do we do to make our converse? Reverse it, switch it around. So we're going to say if a point is, how are we going to turn this around? If it is equidistant from the sides of the angle, then it is on the bisector of the angle. And I'm going to say it's on the angle bisector. So what that tells us, we're just going in reverse. If we know that these distances are the same, then that point has to be on the angle bisector. So that's kind of what we did here. We know these distances are the same, so that point where those two x's, where they cross each other, has to be on the angle bisector, and that's why we draw our line through that. If we know that these two distances are the same, that tells us this point has to be on this angle bisector. All right, we good there? Okay, let's look at an example. Our picture is going to look just like the one we just drew, basically. So here's my angle. Here's this. Before I do anything else, I'm just going to. What do we know about segment LO? It is the angle bisector, right? Because each of these two pieces, each of these is the same. LO is the angle bisector. All right, so that could be important to what we're doing. All right, so let me draw in a couple more segments here. All right, so point O is on the angle bisector, So what does that tell us about these two lengths? They are, the segments are congruent, the lengths are equal. And we have to be careful that we have this 90-degree angle on both of them. We have to make sure we're measuring at a 90-degree angle on both sides. So those lengths are equal. So if our problem says, I'm going to say M and P, find the length of OP. What do we do?
Do like 6x equals 3x plus 12. So.
Right? We set these two equal to start, right? We know those two segments are the same. So we want to find x first. So this is, in disguise, this is saying find x. And we're going to do that first. And we do that by, we realize that these two are equal. 6x equals 3x plus 12. So we find x. This one, whoops, not 2, 12. Subtract 3x. So 3x equals 12, and x equals 4. And then to find OP,
You just
plug it 4 in there. So we get 3 times 4 plus 12 equals, 3 times 4 is 12 plus 12 is 24. And there's my answer.
plug 4 into x. 6x.
Sure. So we know that both of these are equal. 6x equals 3x plus 12. So Porter says it's easier to, maybe a little easier to just do 6 times 12, 6 times 4. 6 times 4 is 24. And we're set. Either way works. All right, questions there? Okay. All right, so this is what the problems we're going to do out of our book. We will start talking about, I will show you how to start on the dynamic activity during class. But you'll need to do that. And the lesson quiz, and I'll show you how to get to that as well. That's 3 questions, 3 multiple choice questions. And that's in the online textbook also. So all this that we'll be working on.